Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about the power series representation of a function. So before we start with the lesson, let's take a second to just remember the geometric series that we talked about in one of the first lessons that we had on series. So if you remember, the geometric series was basically spanning from n equals 1 to infinity, and it was basically consistent of a constant a, and then we had this rate, which was to the power of n minus 1. We went on to find out that the sum of this series, which was basically going to be a plus a times r plus a times r to the 2, and then so on, we figured out that the sum was going to be a over 1 minus r. Now, if we look at what we're doing now with the power series, well, these two kind of closely resemble each other. So if we look at the power series, well, it spans from n equals 0 to infinity of x to the n. And what x to the n is, well, it's 1 plus x squared, and so on. So they actually look fairly similar, right? Here are your constants. Here is your constant. In this case, it's a 1 times this rate, which is r. In this case, it's n. And then here's the squared. So these two actually look alike. And the sum, well, it can be expressed in a very similar way. This series, the power series, has an a value of 1. The rate is equal to x, right? So it would be fair to say, well, that the sum is going to equal to the same thing pretty much. It's going to equal to 1 over 1 minus x. So we have now derived a sum for this power series. And basically, we're going to be using this right here as a basis for representing functions in power series like form. This right here is going to help us convert functions to a power series, basically. To find the power series notations for functions, there's kind of two steps. It's really not that difficult. Basically, all we got to remember is this little thing right here. And again, I've showed you how we can come back to that. If we really need, we can just think about our geometric series and then from there sort of work forwards to find the power series sum. And then it would be equal to 1 over 1 minus x. And then we just need to remember that, and we need to try and represent the function close to this format. And obviously, I'm going to give a few examples and show you how we're going to do that. So let's say we are given this function right here, and we are asked to find the power series notation for this function. Well, like I said, we're going to try to portray this function in as close to this format as we can. And as we can see, it's already sort of in that format. Perhaps we can make one change right here, and that we would include this minus, and then this would be minus x squared. So if this right here was equal to the series of x to the n, right? Well, we could see this x is related to this x right here. But in this case, this entire piece right here is going to be that x value. So this is simply going to be equal to the same thing. It's going to equal to the power series starting from n equals 0 to infinity. And in this case, x is going to be minus x squared to the power of n. Now we can go on to simplify this. It would just be equal to minus 1 to the power of n, and then it would be x to the power of 2n. And that's basically it. That's all there is for this lesson on power series notations for functions. We will go on in a little bit more depth in later lessons, but this is essentially all there is to it. So now on to a slightly more challenging example. So here is the new function that we're going to be dealing with, and let's say that we are asked to put this or to find a power series representation of this function. Again, we want to try to represent this function as close as we can to something like this. So let's go ahead and do that. First, what we want to do is we need a 1 in the numerator. So how can we do that? Well, if we factor out x cubed, we're going to be left with 1 over x plus 2. And now that's looking a little better. Now, as we can see in the denominator over here, we have the constant minus the variable. So it's better to rearrange this and put the constant first. And then we want to do minus the variable, which in this case would be minus x. Now, as you can see here, we need a 1. And the way we can do that is by factoring out a 2 from here. So let's go ahead and just factor out a 2 in the denominator and be left with 1 minus x over 2. Now this function is looking a lot closer. However, we do have this half that we can additionally factor out and get an even closer representation basically making it look a lot closer to this. There it is. We have factored out all these unnecessary terms, and we have gotten this part looking very closely to this. So now, because we know this is equal to the series from n equals 0 to infinity of x to the n, this being x and it belonging here, well, in this case, the x is going to be this portion right here. So we are simply going to say, well, this is equal to, we're going to keep these constant values outside right here. And then inside these brackets, well, this is the series sum from n equals 0 to infinity. And then what we want is this x value is now going to be minus x over 2. And then this is going to be to the power of n. So this series can be simplified a little bit more. So we're going to leave these for now. And because of that negative, well, it's going to be minus 1 to the n. And then this is going to be over 2 to the n. And we're going to have x to the n. Basically what I've done is I've just distributed this n words to every term that we have inside of these brackets. We have a minus 1, we have a 2 in the denominator, and then we have the x value itself. And now we want to get rid of these constants right here. So what we can do is we can actually bring them inwards. Essentially, when we bring this inwards, well, we're going to have a sort of power times a power. And when we have something like a to the power of x times a to the power of y, well, we can conclude that it's just going to be a to the power of x plus y. So the same thing is going to apply here, and the same thing is going to apply with this 1/2. So the 2 is just going to go down here. So let's bring this 1/2 in, and we're going to get from n equals 0 to infinity. This minus 1 stays untouched because we don't have any negatives. The 2, on the other hand, well, there's another entry of a 2 here, so it's just going to be 2n plus 1. And then obviously this x, well, x cubed times x to the n, well, that's just going to be x to the n plus 3. And this is the final power series representation of the function that we started off with. So again, nothing really too difficult. We just factor out terms, make it look something like this right here, and then we simply just plug in our x value that we have into our series and then kind of slowly bring in these terms inwards. So now on to differentiation and integration of power series. This stuff is actually kind of applicable in the computer science scene, and I've seen it in some examples behind like algorithms for linear regression, if you get to like maybe like very basic machine learning and stuff. So this is used, actually I've seen it used, so I do find this pretty applicable. So maybe you're interested in that stuff, maybe this is the kind of section that you would want to pay attention to. Basically, if we have this power series right here, and we say that it has a radius of convergence that is greater than 0, right? And then we also have its associated function with it, which is basically kind of us, in a sense, like unwinding this, basically going through all the iterations of n. We're ending up with this function right here. Now, this function is differentiable, and obviously it is continuous because it's differentiable on this interval here, which is the standard interval that we have, except one thing to note is that these brackets are exclusive. The thing to take away is that the derivative of this function, well, we're just going to take term by term derivatives. So before this, well, we had c0. That's just a constant. So the derivative of a constant is going to be 0. Then we have this c1, which is a constant times x minus a. And if we take the derivative of that, well, we're just going to get that constant. In this case right here, we are going to apply chain rule. So we're going to drop this 2 right here, and then we're going to keep our constant, and then obviously it's going to be, we have a 1 over here, and then because it's chain rule, well, we're going to multiply by the derivative of x minus a, which is just 1. And likewise for all of the other terms, the next term we're going to have a 3 up here. We're just going to drop the power, subtract 1, and that's it. So nothing really too difficult. The more general formula for the derivative of a series is right here. Again, we are just going to drop this power right here and subtract 1. Now for integrals of this function, again, integration stays the same. We're just going to have like part by part integration. So here's the constant that we always include for integration. So for c0, before we had, it was basically c0 times x minus a to the 0, but now we're going to add 1 to the power and then divide by 0 plus 1. So it's just going to turn into c0 times x minus a. And like you can see, we do this for every single term. So c1 before had a power of 1 over here, but now we're going to add 1 to that power and divide by it. So that's why we have this 2 here and dividing by 2 there. And we're going to do that for every single term, as you see. And the more general way to write the integral of a function, especially this series, is right here. Again, we're simply going to add 1 to the power and then divide by that sum. And this should not be anything new. These are very basic integration and differentiation laws. So really nothing new. The other key thing to note is that the radius of convergence stays the same for both the derivative of that series and the integral of that series. So it doesn't change. Let's say for this example, we are asked to find the power series representation of this function tan minus 1 of x. One of the things that you can notice right away is that the derivative of this function is actually going to equal to 1 over 1 plus x squared, which looks very close to the format that we want, which is going to be 1 over 1 minus x. So we can use the fact that if we take the integral of the derivative, we're just going to be left with f of x. So if we take the integral of 1 over 1 plus x squared, well then we should technically end up with this. Now, if we were to find the power series representation for this, which we already know how to do, then we're able to find the power series representation for this. So what are we going to do? Firstly, we're going to break it down and start off by finding the power series representation for this. And again, that seems fairly simple because we already know how to do that. So this is just going to equal to the series sum to infinity from n equals 0. Obviously, the x value in this case, it's going to be minus x squared. And then this is going to be raised to the power of n. So we can go on to simplify this by taking the integral of the same series. However, we're going to have minus 1 to the n, and then this will be x to the 2n. And now we want to take the integral of this series, which we just learned how to do. So we know that we're going to, the constant stays untouched. All we're going to do is we're going to take that x value, we're going to add 1 to its exponent, and then we're going to divide by that sum. And this right here is all that that series equals to. So you can see how by breaking this kind of complex function down into its derivative and then taking the integral of it will help us kind of smoothly find the power series representation for this function. So that's it for today's video on power series representations for functions. Hopefully you guys enjoyed the video and have learned something from it. If this video has helped you out at all, please like and comment as to what I helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I'll catch you guys in another video.